Hi, this is part 2 of linear transformations. So we're going to discuss an example here, but let's remember that the definition of a linear transformation is that we assume it maps one vector space U into vector space V, and we assume two things, that the evaluation U plus U2, remember U is closed under addition because it's a vector space, this evaluation of this here being a member of U, that evaluation is the same as T evaluated U1 added to T evaluated U2, and also the other property defining here a linear transformation, the other property that we use to define linearity, if you will, is that T evaluated alpha U is alpha times T of U. This is assuming assuming that alpha is a scalar, it's a complex number, and also assume that U1 and U2, these are all members of U. Okay, so what we're going to do now is to illustrate some of these definition of linear transformation. So let's assume that U is C3. So we're going to assume this domain here is C3, and V, the codomain, is C2. So these are vectors with two entries. And that means that a member of the domain here, this vector here is a member of the domain, which in this case we're assuming that domain equals C3, and that's what C3 we know is a vector space, and this is assuming C3 has nothing else is being specified here, so we assume that it has the usual operations that we call addition and scalar multiplication defined in C3. And so this is the definition of the map, meaning that if it maps C3 into C2, the map takes in the input, this vector here, x1, x2, and x3. This is considered the input of the map, of the linear transformation. And this other vector, so this other vector, which is the output, is a member, right? This vector is the output, and this is clearly a member of C2. So that's another way of thinking of linear transformations. You think of linear transformation as the linear transformation, some kind of box, all right? And so the box has an input. That input comes from the domain, and then the box produces or yields an output, and that output is in the codomain, right? So input is in the domain, and the output is in the so-called codomain. In this case, the input, whatever is coming in, is a vector with three entries, x1, x2, and x3. And then here the output is going to be a vector. I'm just going to write here like two dots, a vector that has two entries. The first entry is defined as twice the quantity, the first quantity in the input plus the third quantity in the input. And the second entry is the -4 multiple of the quantity in the second location, here the quantity that appears second in the input. So let's assume that we have x in C3 and y in C3, so that means here that x, we're assuming that x being in C3 has entries x1, x2, and x3, and then we're also going to assume that y has entries y1, y2, and y3 because we're assuming that these are members of C3, which is the domain. It's the vector space defined as the domain. So if we consider the sum of x1 plus x, plus x plus y, we're considering the sum of two members of C3, and here this addition is the usual. This here would be the usual addition operation in C3, the usual addition operation in C3. So when we add these two members of C3, we're coming up with a new vector okay, a new vector that has the first entry equals x1 plus y1, the second entry is x2 plus y2, and the last entry is x3 plus x3. But now I would like to go back and actually apply the definition of this linear transformation. And so here's a good opportunity to remember that the definition of this transformation, I'm going to write this slightly with different notation. I'm going to say that this being defined on u1, u2, and u3, okay, that this is equal to, for the first entry, 2u1 plus u3, and in the second entry, that's equal to minus 4u2, okay? So that means that the transformation, when evaluated, we're going to have a vector that has only two entries. The last entry would be minus 4 times the entry that was second. So this would be minus 4 times x2 plus y2. That would be the last entry. That's what this says. Minus 4 ut means take whatever entry you have on location 2, multiply by negative 4. That's what we get here as the second entry. The first entry, by a similar reasoning, is computed by 2 times the first entry plus the third entry. Okay, so that gives us this expression. And what we can do from here is that we just do simple algebra, like the good old days. So 2 times x1 plus 2 times y1, and then we add that to x3 plus y3. Similar here in the second entry, minus 4 times x2 minus 4 times y2. Okay, so this is what this looks like now. And so one thing that we are doing in this step, so remember here on what we would have is 2x1 plus 2y1 plus x3 plus y3. That's what we would have in the first entry. And so what we're doing now is collecting the terms that have x. So you can put those terms with x first, and then the terms with y second. And similar here, when we multiply, so this would give us minus 4x2 minus 4y2. So we can collect terms with x first, terms with y second, and then we can split them. So it turns out that if we look at first and second entry here, we could write that as a vector on its own, which is added to another vector of its own. But this definition here, this definition of addition, this would be the addition operation. Okay, the addition operation in the vector space C2. And because this is adding two things in C2, we can note that this first portion here is the evaluation of the transformation at x1, x2, and x3. Okay, and so similarly, the second part of this addition is the evaluation of the linear transformation t at y1, y2, and y3. So what this tells us is that when t is evaluated at x plus y, that is equal to t evaluated at x added to t evaluated at y. And this is part 1 of the definition of a linear transformation. So the other thing that has to be verified, that has to be confirmed, is the property that has to do with scalar multiplication. So we, to define a linear transformation, we just established that addition under the linear transformation, that there is something that relates to the addition operation. And remember, in this case, we're assuming that the input to the transformation t, that input is x plus y, and then here we assume that that output is t of x added to t of y. Okay, so this first property has to do with addition. The second property has to do with scalar multiplication, and first we need to note here that this x, remember, we're assuming that x is a member of C3, and we're going to write x as x1, x2, and x3. Okay, So when we consider alpha times x, there is alpha multiplying x. This is now x. And by definition of scalar multiplication on C3, that vector alpha times x has entries here, has entries alpha x1, alpha x2, alpha x3. Okay, and so we evaluate the so we evaluate the transformation with this vector that has entries alpha x1, alpha x2. And so the definition of the transformation is first entry is going to multiply 2 times the first entry, okay? And it's going to add the last entry. So that's exactly what's happening. That's exactly what's happening here. And then the second entry will be -4 multiplied by the entry on location 2. And so in doing so, we can basically pull alpha here, alpha as a common factor. Excuse me. It's a common factor, right? So that's the idea with these terms with alpha, and then we can really, because of the definition of scalar multiplication in C2, right? This equation here follows from scalar multiplication in C2, and therefore this is equal to alpha times the transformation evaluated at x. Okay, and so this verifies the second property. So remember, the linear transformation is something, linearity here, linearity or linear functions, these linear functions we're calling transformations, rely on addition and scalar multiplication, right? So in this example, we have just verified that this transformation T satisfies property 1 regarding addition and property 2 regarding scalar multiplication. Therefore, T, we would say, we conclude that T is a linear transformation.